If you open a map on your phone right now, the blue dot representing your location is usually accurate to within about 10 feet. It's making an educated guess using a combination of GPS, cellular networks, and Wi-Fi signals. For most daily tasks, a 10-foot margin of error is perfectly acceptable. It's enough precision to help you navigate traffic or find the entrance to a local business. But if you're laying high-pressure underground pipelines or mapping property boundaries, being off by several feet is a disaster. The professional standard for building modern infrastructure requires spatial accuracy down to a range of 10 to 25 millimeters, roughly the width of a finger. Engineers bridge this gap using specialized technology, like this high-accuracy GNSS receiver, mounted on a stabilizing tripod to maintain a steady reading. Achieving millimeter precision from satellites 12,000 miles away relies on a system's ability to systematically identify and strip away layers of environmental error. While GPS is often used as a universal shorthand, the Global Positioning System is actually a single navigation network operated by the United States. Professional receivers utilize GNSS, Global Navigation Satellite System, which allows them to tap into multiple global satellite constellations simultaneously. Instead of relying on a sparse web of 4 satellites, a GNSS receiver expands to lock onto a dense network of 15 or more. This provides better spatial geometry and a stronger mathematical baseline for the receiver. The next layer of precision involves tracking multiple frequencies. High-accuracy GNSS receivers track multiple distinct frequencies from the same satellite. As these signals pass through the atmosphere, they slow down at different rates. By comparing arrival times, the receiver calculates the exact atmospheric delay and finds the true distance. Utilizing more satellites and frequencies eliminates major geometric and atmospheric distortions, but minor discrepancies remain that require an on-the-ground solution. That on-the-ground solution is a real-time kinematic, or RTK setup. This is the surveyor's primary tool for stripping away the final layers of location error. An RTK setup requires 2 components, a stationary base station and a mobile rover carried by the surveyor. The base station is anchored to a completely fixed, mathematically verified geographic location. Knowing its true position, the base station compares actual coordinates against where satellites claim it is, revealing the exact margin of error. It broadcasts this differential correction to the surveyor's rover, which instantly adjusts its position to achieve centimeter-level accuracy. RTK technology achieves absolute precision by using a grounded mathematical truth to correct the shifting interference from the atmosphere. The final output of this process is a rich data format built on strings of information called NMEA sentences. These sentences contain critical metadata, including horizontal and vertical accuracy metrics, the specific fix types, and the total number of satellites utilized for every point collected. To ensure absolute certainty in the field, surveyors employ a quality control technique called GPS averaging. The surveyor takes multiple continuous readings of a single coordinate over time. This allows the software to rule out anomalies and average the data into a hardened absolute truth. This depth of metadata allows engineering organizations to trust their maps, proving that every collected point meets strict scientific standards. Back in the physical world, this hyper-accurate data is used to establish ground control markers across a job site. Surveyors establish a reliable matrix of these control points using their GNSS rovers, creating a high-precision skeleton for the site. This matrix serves as the foundation for modern aerial mapping. A UAV drone, like this Sea Astral Braymore, is launched to capture thousands of overlapping high-resolution images. The precise GNSS coordinates from the ground markers allow modeling software to stitch those aerial images into a map with 1 to 200 scale accuracy. High-accuracy GNSS receivers actively calculate, compare, and strip away environmental interference, providing the unshakable mathematical anchors required to digitize and build our world.